Okay, so hopefully you're working on homework 10. That's due next Tuesday, or this coming Tuesday, the 14th. We will have one more homework assignment assigned to you that will be due after the Thanksgiving break. So this is the last one before Thanksgiving, I believe, because the week after that is Thanksgiving, right? Yeah. Okay, so chapter 15. There is really a lot of terminology that we have to go through, so I apologize. There's going to be a lot of just text on slides, but there is so much that we need to define before we start talking about how to use these principles. So first off, what is a fuel? A fuel is any material that you burn to release energy, and in most cases it's a thermal energy. Hydrocarbon fuels are the most common types of fuels that we encounter in engineering practice, particularly when we're looking at using them as a combustion source for adding heat to a system. And they're some combination of carbon and hydrogen. So it's usually in the form of C something, H something, and a lot of times there's also a hydroxide in there too with an oxygen term. And so hydrocarbon fuels that we encounter in real life are coal, natural gas, kerosene, propane, diesel, all of those things that we consider to be just normal fuel sources are some combination of carbon, hydrogen, and in some cases oxygen and sulfur. A chemical reaction in which we use oxygen in order to oxidize a fuel is considered combustion. So in order to have a combustion process, you need both a fuel source and an oxygen source or an oxidizer. And any components that are coming into the system prior to combustion happening are called the reactants. And in most cases, the reactants are actually reacting. There's some cases where there are inert reactants that come into the system. But when they exist prior to combustion, they're called a reactant. And then what comes out after combustion is called a product. So we're going to be looking at two sides of an equation with the reactants and the products, and balancing the molar numbers on each side of the equation. And combustion must occur at or above the ignition temperature of the fuel. Okay, so this ignition temperature is the temperature at which the fuel will ignite. It also needs to be in the presence of an oxidizer in order for that to happen. So two things lend itself to combustion. One is oxygen. The second is the temperature. So you need both in order for the fuel to actually combust. So oxidation in its most general form is just oxygen in the O2 form. And it's used in combustion processes, but it's pretty rare that pure oxygen is used because it's not necessary to use that much, that high of a percentage of oxygen. We can use just general dry air because dry air has 20%, 21% oxygen and about 79% nitrogen. So the nitrogen is just there because it's a component of air, and it's really just the oxygen within that air that we're using as the oxidizer for our reaction. So when you're talking about a fire needs air to burn, really it needs oxygen to burn, and air has enough oxygen in it that it can oxidize or cause this, it can be a catalyst for this reaction. Because air is 21% oxygen and 79% nitrogen, when we analyze this oxidation equation, it comes in with 1 kilomole of oxygen and 3.76 kilomoles of nitrogen. So that 3.76 term comes from 79% divided by 21%. So that's where the 3.76 comes from. So when we're analyzing any kind of an oxidation equation, we just assume that for every kilomole of oxygen, we're going to have 3.76 kilomoles of nitrogen. So that gives us a total number of kilomoles of 4.76 for air. So we can look at this two different ways. We can analyze every equation where we look at the oxygen and the nitrogen separately, or we can just look at it as air, because air actually contains other inert gases besides oxygen and nitrogen, but those are the two primary components that we consider and are worried about. The air-fuel ratio is the ratio of the mass of the air to the mass of the fuel in our combustion reaction. Certain fuels require a certain air-fuel ratio in order for the combustion to be complete. So we'll talk about that in a minute, but it's important, this air-fuel ratio is important because if we don't have enough air in our system as we're trying to combust these gases, we'll have uncombusted byproducts at the end of it, which lends itself to pollution. It also reduces the amount of thermal energy we're getting out of these fuels as we're putting them into our system. So we want complete combustion. We want to have the right amount of air so that we can achieve complete combustion. Because there are some cases where if you have too much oxygen in the environment, the combustion occurs too rapidly, and it's also an incomplete combustion because certain products burn up quicker than others, and then others are exhausted in the exhaust. Okay, so when we look at combustion reactions, we also apply the first law of thermodynamics, which is conservation of mass. So the total mass of each element within that combustion equation is conserved. The total mass of the reactants has to be equal to the total mass of the products. And then the total number of atoms of each of those these elements that are coming into the equation also has to balance on either side of the equation. So when we do these chemical balances on either side of the equation, these two tools allow us to figure out some unknowns in our products. So if we know what's coming into the combustion chamber, we know the amount of air that we're adding, we can calculate the air-fuel ratio, and in turn we can figure out the combustion byproducts and how much is there. However, the total number of atoms of each element is conserved, but the total number of moles is not necessarily conserved. So that's important to remember. And the chemical composition of the products will not necessarily be the same as that of the reactants. So you may have some combination of a hydrocarbon fuel on one side of the equation, you combust it with oxygen and nitrogen, and then on the other side of the equation in your products you might have water and carbon dioxide and carbon monoxide and hydroxide coming out. So what you put in once it's combusted, in some cases like nitrogen will come through the equation, but other products are a different combination of elements. Okay, so let's talk about the difference between a theoretical and an actual process. In theory, every combustion process is complete, that we have this stoichiometric amount of air. We'll talk about that term in a minute. And that it's a perfect scenario where all of our carbon is combined with oxygen to become carbon dioxide. All of the water also all of the hydrogen also bonds with an oxygen molecule to become a water byproduct, and that sulfur becomes sulfur dioxide, which in and of itself is not an ideal thing to have because it contributes to greenhouse gases and acid rain, but it's better than having some of the other free elements just sort of coming out in the wash. So it's an incomplete process if we have any free carbon, hydrogen, carbon monoxide, or OH molecules at the end of the combustion process. Anything other than that, if we just simply have carbon dioxide, water, and sulfur dioxide, we consider it to be complete. So as mentioned before, incomplete combustion can be caused by not having sufficient oxygen, or if we have too much oxygen, if there's insufficient mixing so that this process occurs in a non-quasi-equilibrium way, we can also have incomplete combustion if there's not enough time, or dissociation where these molecules, because they're encountering such a high temperature, they begin to split before they actually undergo combustion. That can also cause incomplete combustion because those molecules are dissociating before we want them to. The energy is not released during combustion process, it's prior because the temperatures are too high. The minimum amount of air needed for complete combustion is called the stoichiometric air, or in some cases it's also called the theoretical air, or another term is the necessary air. Okay, so you may see any combination of those three terms when you're looking at problem statements, that it will say it contains the stoichiometric amount or the theoretical amount or the necessary air. And an ideal combustion process with this amount of theoretical or stoichiometric air is called a stoichiometric combustion or a theoretical combustion. So the theoretical combustion is the perfect scenario where we have exactly the right amount of air and everything combusts completely. If we have greater than the needed amount of air, it's referred to as excess air. And in some cases, having excess air is a necessity in order for this combustion process to be assured to be complete, because the theoretical amount of air may be insufficient in a case where there isn't enough mixing, or if your temperatures are slightly too low. So in some cases, the excess air is necessary in order to assure complete combustion. And if we look at 50% excess air, that's the same as saying it's 150% of the stoichiometric air or the theoretical air. And then if the quantity of air is less than needed, it's referred to as a deficiency of air. And a 10% deficiency is equivalent to only having 90% of the theoretical air that we need for this combustion process to occur. Okay, so lots of terminology. Let's now do some examples so we can see how this works in practice, and how we apply our knowledge from chapter 13 with balancing these equations on either side. Okay, so we have a fuel mixture which by mass is 60% methane and 40% ethanol. And it's burned completely, so this is a complete combustion process with theoretical air. So we have the exact right amount of air for this combustion process to be complete. If the total flow rate of the fuel is 10 kilograms per second, we need to determine the required flow rate of the air. So the fuel is coming in at 10 kilograms per second. We want to know the mass flow rate of the air. And because this is deemed a complete combustion, what would be the products at the other end of this combustion process? Okay, so we'll have carbon dioxide, water, and in many cases, because we're combining with air, we also have this nitrogen at the end. Okay, so our products are going to be some combination of carbon dioxide, water, and nitrogen. We're not going to have any free carbon. We're not going to have any hydroxides. We don't have to worry about carbon monoxide either. Okay, but first we have to figure out, so when it says it's 60% by mass, what type of analysis is that? Is it gravimetric or a molar analysis? Okay, it's gravimetric, right? So in order to perform these combustion equations, everything has to be in molar form. So we'll first need to convert this 60% by mass to a 60% by, or to a whatever percent by volume. And in order to do that, we need to determine the molar numbers for each of these and the molar fractions. Okay. But we have to start looking up some things in tables A1 and in A27 because they're not all in one table, which is a little bit frustrating actually. So we want to know the molar masses for carbon, hydrogen, oxygen, and air. And we can also look it up for, I guess, nitrogen if we want. So what is the molar mass, M, in kilograms per kilomole of carbon? Okay, and we're just going to call it 12. What about H2? 2. Yes, we're rounding everything. Oxygen. That might be one you have to get in the other table. 32 for O2. Yeah. Air is 29, and nitrogen is 28. So that's all in kilograms per kilomole. Okay, so now we need to figure out the number of moles that we have in each of these. So the number of moles in CH4 is equal to, if we assume just some 100 kilograms mass, it's going to be 60 kilograms divided by the number of each of these elements times their molar mass. So carbon, there's one of those times 12 kilograms per kilomole plus H4, there's 2 H2s times 2 kilograms per kilomole. So it's important to make that distinction with oxygen, hydrogen, and nitrogen that it's diatomic, that we if it's an H4, there's 2 H2s in an H4. Okay, so we find the molar number for that is 3.75 kilomoles. And then we do the same thing for C2H6O, where it's 40 kilograms divided by 2 times 12, so that's our carbon, plus 3 times 2, which is our hydrogen, plus 32 over 2, because this is a single oxygen, whereas that's O2. So we find the molar number for this to be 0.870 kilomoles. If we add those together, we find a total molar number for the mixture is 4.62 kilomoles, which we can then use to find our molar fractions. So the molar fraction is equal to the number of moles divided by the total moles of the mixture. So we're going to have 3.75 over 4.62 and 0.870 over 4.62. So that gives us a Y value here of 0.8117 and a Y value here of 0.1883. Okay. So now we can rewrite our equation in terms of these molar fractions that we determined. So we have 0.8117 CH4 plus 0.1883 of C2H6O. Yes? It's the molar fraction. Yeah, so what we were given was like a mass fraction, so 60% by mass. We wanted to convert it into a molar fraction. Yeah, yeah. If you add these two together, they equal 1. Yeah. Okay, so we have those are our products, but we need to react it with air. And so we have this theoretical amount of air multiplied by O2 plus 3.76 N2. So these are all the reactants. Okay, so then the other side of the equation will be our products, that we have some amount of CO2 plus some amount of H2O plus some amount of nitrogen. And because we know these molar fractions have to balance on either side of the equation, we can set some of these components equal to one another. Okay, so we have, if we look at our carbon, we have 0.8117 on the reactant side of the equation is equal to, there's only one carbon here, is equal to X on the other side of the equation. So this X value will be equal to 0.8117. Okay, next we look at our hydrogen. So we can say that it's 2 times 0.8117 plus 3 times 0.1883. So that's from here. Yes?
What about the carbon in...
Oh yeah, I forgot that one. Sorry. I should look at my notes. Okay, so 0.8117 plus 0.1883 times 2 is equal to X. Sorry about that. Okay, so then with hydrogen, we have those two molecules. We have 2 times 0.8117, 3 times 0.1883 is equal to, on the other side of the equation, Y. So we find X is equal to 1.188 and Y is equal to 2.188 if we do the math on those. Okay, so now we can look at oxygen. We can look at it as an O or an O2, however we want to do it. In this case, we can say it's 0.1883 over 2 plus this theoretical amount of oxygen here is equal to x plus y over 2. Okay, so if we sub in x and sub in y, we can solve for this A theoretical is equal to also 2.188. And then we look at nitrogen, that on this side of the equation we have A theoretical times 3.76 is equal to Z. So Z is equal to 8.227. Okay, so this is the process and procedure for finding all of the coefficients in front of your terms in your equation. So we're balancing the masses on either side of the equation by performing this analysis.
Does that O2 take into account the oxygen from the ethyl alcohol as well?
There's just this one, so 0.1883 over 2, and then that, right? This is this one.
Okay, yeah.
That's a 2. Can't read it very well. Okay, so now we can rewrite our equation. I'm just going to erase some of this stuff so I have room to write. That we can put in some of these terms, replace x, y, and z, and this A theoretical with the proper proper things. So this is 2.188. This CO2 is 1.188. And in front of H2O is 2.188. And in front of the nitrogen, 8.227 and 2. Okay, so again, we have our reactants and then our products. Okay, so this is all leading us to be able to find the air-fuel ratio. So the air-fuel ratio is equal to the mass of the air divided by the mass of the fuel. So in order to find the mass of the air, we look at this part of the equation. So we have 2.188 multiplied by the molar mass of O2, which we looked up before was 32. And then the molar 2.188 times 3.76 times the molar mass of nitrogen. We can do it that way, or we can just say 2.188 times 4.76 times the molar mass of air, which is 29 kilograms per kilomole. So we can do it either way. We can look at the oxygen and nitrogen individually, or we can say this is air and just calculate it that way. You get slightly different answers, but they're very close. So we find that looking at that, the mass of the air is 302.03 kilograms. Now we want to find the mass of the fuel, so that's this part of the equation. So we have 0.8117 multiplied by this carbon, which is a 12 kilograms per kilomole, plus 2 times H2, the molar mass of H2, which is 2 kilograms per kilomole, plus 0.1883 times 2 times the molar mass of carbon, which is 12 kilograms per kilomole, plus 3 times the molar mass of hydrogen, which is 2 kilograms per kilomole, plus 32 kilograms per kilomole for oxygen over 2, or in other words, 16 per single monatomic oxygen. Okay, so the mass of the fuel is equal to 21.649 kilograms. So now we find this air-fuel ratio, 302.03 divided by 21.649 and gives us a value of 13.95. Okay, so now we can say that this air-fuel ratio is equal to the mass of the air over the mass of the fuel, but it would also be equal to the mass flow rate of the air over the mass flow rate of the fuel. So we can say that the mass flow rate of the air is going to be equal to the air-fuel mixture times the mass flow rate of the fuel. So we plug in the numbers for that. The mass flow rate of the fuel is 10 kilograms per second, which means our flow rate for our air has to be 139.5 kilograms per second. So that's the mass flow rate of the air in that problem. Okay, it's very easy to get lost in some of these calculations. You have to be very methodical and detailed in how you do it. I know a lot of you like to just jump steps and type everything into your calculator without writing it out first. I highly recommend you write these equations out so that if you miss one of these terms, you miss an oxygen, you miss something else, then you can go back and look and see where something was missing. Because if you just put down numbers because you're putting everything in your calculator, it's going to be hard to keep track of what you're doing. Okay, any questions on this process? So in this example, it showed how to go from a molar analysis or from a mass-based analysis to a molar analysis, and then using that molar analysis to figure out how much of what mass flow rate of air is required to get that complete combustion with theoretical air. Okay, so we're going to add an additional little bit of complication. So now we have a reaction that's burning to completion, again, but we have excess air. We also are going to do this with non-dry air. So this air has some humidity associated with it, which means that we are going to try to figure how much of the water vapor is going to condense out of these byproducts if we cool the gases to 25 Celsius. So it's kind of like combining what we were doing with last chapter with what we were doing in chapter 13. Okay, so this is where we need to know how to use a stoichiometric chart. In this case, we don't look it up, but we need to know and understand those principles involved. Okay, so in this case, it's 45% CH4, 35% H2, and 20% N2. And it's a volumetric analysis, which is good because we don't have to go through and calculate the molar numbers for everything. We can just use those volume percentages in our equation as molar fractions if we assume it's 1 kilomole of fuel. So if we were to rewrite this, it would be 0.45 CH4 plus 0.35 H2 plus 0.20 N2 plus, we now have 30% excess air, so it's the theoretical air times 1.3. So it's 130% of theoretical air is 30% excess times O2 plus 3.76 N2. So again, it's complete combustion. What would you expect to be on the other side of the equation? Anything? So we'll have some CO2 plus some water plus some nitrogen plus, because we have excess air coming in on this side, we're going to have some 30% excess air coming out the other side. And we're just going to look at that in terms of the O2, and then it'll work itself out, figuring out how much nitrogen is excess. Okay, so we apply the same principles where we look at the coefficients on either side of the equation to balance everything out. So in this case, we have, if we look at carbon, we have 0.45. That's the only carbon term, is equal to X. If we look at hydrogen, we have 2 times 0.45 plus 0.35 is equal to Y. So Y is equal to 1.25. X is 0.45. Then we can look at our oxygen. So we have 1.3 times the theoretical amount of air times our oxygen is equal to x plus y over 2 plus 0.3 a theoretical. So we can solve this for a theoretical is equal to 1.075. And then we last look at nitrogen. So we have 0.20 plus 1.3 times 3.76 is equal to Z. Let's see, 1.3 times 3.76 A theoretical is equal to Z. So we plug in A theoretical, solve for Z is equal to 5.455. 5.455. Okay, so we can rewrite this equation in longhand. 0.45 CH4 plus 0.35 H2 plus 0.20 N2 plus 1.3975, that's the 1.3 times A theoretical, O2 plus 3.76 N2 goes to 0.45 CO2 plus 1.25 H2O plus 0.3225 O2 plus 5.455 N2. Okay, so if we have 1 kilomole of fuel, and we look at this other side of the equation, we add up all of these values, we find that we have 7.4775 kilomoles of a product. And of that, 1.25 is water. Okay, so what we're saying is that with these byproducts, we're going to cool them, and we're going to see how much of this water, compared to the mass of the total mass, condenses out at 25 degrees Celsius. Okay, if we had a stoichiometric chart for this particular fuel, we would be able to just use a chart. But this chart is for air. We can't use that chart and look up the values, so we have to do it another way. But some of the same principles apply. We can still assume that this is an ideal gas. So one thing that we can assume if it's an ideal gas is that the ratio of these two gases, when we're looking at the ratio of the pressures, this was from chapter 13, is equal to the number of moles over the total number, okay, because we're considering them both to be an ideal gas. So if we want to know how much water has been condensed out of this, this process, then we can look at the number of moles initially minus this some amount of water that's being condensed divided by the total number of moles initially minus, again, the amount of water that's being condensed out. Okay, so the amount of moles in this byproduct will be reduced by how much water is condensed out. So we look at how many moles of water minus how much is condensed and how many total moles minus how much is condensed. And we set that equal to the ratio of the pressures. So at saturation, so when we begin to condense something, our pressure is going to be the saturation pressure at 25 degrees C. And then our total pressure is just atmospheric pressure, 101.325 kilopascals. So the saturation pressure at 25 degrees C is 3.1698 divided by 101.325. So now we have this ratio. We use it to solve for the unknown, N sub W. So we find the number of moles of water that condense out is equal to 1.049 kilomoles. So then we can find the percent of water that has condensed out is going to be the 1.049 divided by 1.25, or how much was there initially. And we find that it's equal to 83.9% of the water will be condensed out if we lower the temperature of the byproducts to 25 degrees Celsius. Okay. Any questions on that example? Yes. Yes. Yeah, because you want to know the pressure of the vapor or the pressure of the water at 25 degrees Celsius. Okay, let's go to the next example. You guys are all glassy-eyed. I know this is kind of boring, but hopefully when you go to do your homework, it will be easier because you have these examples. And on this homework 10, you only have one problem, and it's easier than any of the ones we're doing in class. But on homework 11, you're going to probably have to reference back some of these examples to help you do it. What's really frustrating about the textbook, actually, is it doesn't have any examples of incomplete combustion in the examples that are worked out. So how would you know how to do it if you didn't see some examples done in class? So, okay. So this is another example where we have some hydrocarbon that we're burning with a stoichiometric amount of air. So it's the right amount of air, but the combustion is incomplete, with 5% by volume of the carbon forming carbon monoxide and 5% of the hydrogen forming a hydroxyl. So we need to calculate the apparent molecular weight of the products, which means that we need to balance the right-hand side of the equation and determine what's actually on the right-hand side of the equation so that we can figure out how many moles are there, and then we can calculate the molecular weight. Okay, so the first thing that we want to do when we're looking at a problem that's considered to be incomplete combustion is we solve it as if it were complete combustion to find the molar numbers, or the molar fractions, and then we show what would happen if it were incomplete. Okay, so we're going to balance this equation first. C2H5OH, and it's burning with the stoichiometric amount of air, so it's just the theoretical amount of air times O2 plus 3.76 N2. And then the resultant byproducts in complete combustion, so again, we're looking at the complete case first, X times CO2 plus Y times H2O plus Z times nitrogen. So we're ignoring, right, for now, any carbon monoxide and hydroxyl. If it was hydroxide, it would have a negative. Okay. So let's look at carbon first. We have 2 on this side of the equation is equal to X. That's pretty easy. We'll look at hydrogen. On this side of the equation, we have 3 H2s, because it's an H6 if we count both of those. So 3 is equal to Y. That's pretty easy too. And we look at our O2, and we see that on this side of the equation we have 1/2 plus our A theoretical times 1 is equal to X plus Y over 2. So we sub in X and Y, solve for A theoretical, and we get that A theoretical is equal to 3. Then we look at our nitrogen, and on this side of the equation we have A theoretical times 3.76. On the other side of the equation we have Z. So Z is equal to 11.28. Okay, so we've determined the coefficients that go in front of this equation for the complete combustion. Now we're going to look at it when it's incomplete combustion. And to do that, we use those same coefficients, but we just do a little bit of manipulation on the other side of the equation. So we still have C2H5OH plus A theoretical, which is 3, times O2 plus 3.76 N2 goes to 2 CO times 0.95 CO2 plus 0.05 carbon monoxide. So we're now breaking this component into a 5% by volume mixture of carbon dioxide and carbon monoxide. Then with this Y term, it stays the same, but now we have 0.95 H2O plus 0.05 OH. Plus, we're going to have some unknown quantity of oxygen freed up because they're breaking apart from the carbon dioxide in the water. Plus 11.28 times nitrogen. So now we just need to determine this B component, which if we look on this side of the equation, we have 1/2 plus 3. On the other side of the equation, we have 2 times 0.95 plus 2 over 2 times 0.05. That's for this single oxygen here. Plus 3 times 0.95 over 2 plus 0.05 over 2 times 3. So that's for this oxygen and that oxygen there. Okay, so if we sum all of that up, we find, plus B. So we solve for B is equal to 0.05. So now we can just erase this B and replace it with 0.05 times O2. And all of the other terms in the equation remain the same. Okay, so now we have our equation which represents incomplete combustion. And we want to find the apparent molecular weight of the products. So the products are on this side of the equation. We need to know the molar masses of each of these individual components. So we need to know the molar mass of carbon is equal to 12 kilograms per kilomole. Hydrogen is equal to 2 kilograms per kilomole. Oxygen is equal to 32. Nitrogen is equal to 29. Those are all kilograms per kilomole. Okay, so then it becomes kind of a big, complicated equation. So first, we need to determine the total number of moles. So if we look at our equation, maybe I'll do that on this slide so you can see. So of the products, we have the total number of moles is equal to 2 times 0.95 plus 2 times 0.05 plus 3 times 0.95 plus 3 times 0.05, so we're right here now, plus 11.28 plus 0.05. Okay, so that's just adding up these total number of moles. We find that the total number is equal to 19.33 kilomoles. Okay, so now we need to find the total mass of the products, and this gets a little bit more complicated. But again, if you're being careful and writing everything down step by step, then you don't get quite so lost. So the mass of the products is equal to 2 times 0.95 plus 0.05. So this is for carbon times 12. Then we have 2 times 0.95 plus 0.05 over 2 times 32. This is for oxygen. plus 3 times 0.95 plus 0.05 over 2 times 2. This is for hydrogen. Plus 3 times 0.95 over 2 plus 0.05 over 2 times 32. This is for the other oxygen. Plus 11.28 times 28, which is for our nitrogen. Plus 0.05 times 32. This is for our free diatomic oxygen. So adding all of that up, we get 457.69 kilograms. So our apparent molar mass is going to be equal to 457.69 kilograms divided by what we determined to be the number of moles, 19.33 kilomoles, is equal to 23.67 kilograms per kilomole. And this is a good point to do a reality check. So you look at the components that you have within your system. They range in molar mass between 2 and 32. This is in between that range. It's closer to the 32 side because we have more oxygen and carbon in there than we do some of the other things. All right. So 3 different examples dealing with slightly different scenarios. So whether you have stoichiometric air, whether you have excess air, whether you have moisture in your air, and whether you have incomplete combustion. So it kind of shows you what variables can be thrown in there and how to analyze those equations in slightly different ways. Okay, so any process which involves chemical reactions involves changes in our chemical energy. And up to now, when we performed an energy balance, we were simply worried with simple forms of energy like heat and work. Well, now that we're undergoing these combustion reactions, we also have to consider the chemical energy that comes about due to this combustion process. When we look at chemical energies in our tables, they're calculated based on a standard reference state. So if we go to the back of the book in table A20 something, yeah, so like A26, these enthalpies of formation, which we'll talk about in a minute, are calculated based on a specified reference state. And so that superscript 0 denotes that it's some reference value. And we've seen that before in the ideal gas tables. You remember we have entropy, if you just turn back the previous page, that we have entropy with a superscript 0. That's a reference entropy because we have to take into account how entropy varies with pressure. So this is a similar idea that we're taking 25 Celsius or about room temperature to be a reference state in order to calculate all of these entropy, enthalpy, and Gibbs function values. Because most combustion processes occur in a region that is in its surroundings around 25 degrees Celsius. And then properties at any state can be determined by subtracting their property value at the reference state. So if we wanted to know the actual enthalpy value at some temperature, we would just calculate or look up the enthalpy at that temperature and then subtract off this reference value. So it's similar to what we've done before with entropies. Chemical processes can be categorized as either exothermic or endothermic. So an exothermic process is one which releases heat, and that's what we're doing when we undergo combustion. We're releasing a significant amount of heat, and that's the purpose of combustion as it relates to energy production, is that we're using that thermal energy to then create energy in a more useful form, or not to create energy, but to harness the energy and use and convert it to a more useful form. So because during a combustion process there isn't any work interaction, we're not generally doing any mixing, it's just simply combustion of materials with air, we only need to consider how much heat is generated. So the heat is going to be the difference between the enthalpy of the products minus the enthalpy of the reactants. So the enthalpy of the products are going to be at a higher energy state, higher enthalpy state, because you've just undergone a combustion process and all of that energy was released during the process. And it's also referred to as the enthalpy of reaction or the enthalpy of combustion. So it's actually, when we calculate it, it ends up being a negative value because the enthalpy of the products is lower than the enthalpy of the reactants, okay, because energy is released. So it represents the amount of heat released during this process, and we assume it's when 1 kilomole or 1 kilogram of fuel is burned. And we're burning it completely, and it's also happening at a specified pressure and temperature. So again, when we're using these reference state values at zero, the 0 point is 25 degrees Celsius. If we undergo a process that's at a different temperature or different pressure, then we sometimes have to use those reference states and subtract them off from our actual temperature and pressure. So the enthalpy of combustion has to be calculated or tabulated for every fuel at every pressure and every temperature, which is pretty cumbersome, and it's kind of difficult to get tables that are that extensive. So it's also not very useful to us if our combustion is incomplete, because our products are not always predictable, and we don't always know the exact quantities. So sometimes trying to look at the enthalpy of combustion is a frustrating process. Instead, we can look at the enthalpy of formation, which establishes how much enthalpy. It's almost like looking at it from an exergy point of view. It establishes the enthalpy of a substance based on its current chemical composition. So if we look at the enthalpy of the substance before the reaction and after reaction, using those values, we can calculate how much it changed during the combustion process, and then we can, from that, determine how much energy was released. And for stable elements, if you look in this table A26, you'll notice that carbon, hydrogen, nitrogen, and oxygen, which are stable at room temperature and they don't naturally oxidize at room temperature, their enthalpy of formation is 0. So at that reference point, there is no available energy to undergo combustion. It has to be at a higher temperature. Okay, so then we come to another term called heating value, and this is used to categorize fuels to determine or tell how much fuel is required in order for a certain amount of energy to be released during the process. So the heating value of the fuel when it's burned completely and the products are returned to the state of the reactants, meaning that they're returned back to the initial temperatures or pressures of the reactants, is dependent upon the products themselves, but it also depends on whether or not the water in the end reaction is in the vapor form or in the liquid form. So there's 2 separate heating values for every combination of fuel. One is in which the water is in the vapor form at the end of the process, and one is which the water is in the liquid form. And there's actually some range in between where we have a higher heating value and a lower heating value, and it can end up where some of the water is vapor, some of the water is liquid, but we're not looking at that. We're just looking at the 2 extreme cases in this case. So the higher heating value and the lower heating value. So they're equal to one another, or not equal to one another, but they can be equated to one another using the mass of the water multiplied by the enthalpy of vaporization. So the amount of energy it takes for it to go from a liquid to a vapor multiplied by the mass. When you add that to the lower heating value, then you get the higher heating value of that. So it tells you how much less energy is available because that water's in liquid form rather than in a vapor form. And if you don't know the exact composition of your fuel, you can obtain these values. You can obtain this H sub C value experimentally. So you would need to burn a known portion or quantity of your fuel and then determine how many calories were released during that process. It's all very fun, I know. Okay, so we're going to look at this in reality. So we want to find the higher and lower heating values of a coal from Illinois, which has a biomass analysis of 67.4% carbon, 5.31% hydrogen, 15.11% oxygen, 1.44% nitrogen, 2.36% sulfur, and then there's 8.38% ash, which is considered to be a non-combustible. So when we do our combustion equation, we're just going to ignore the ash, because whatever comes into the system as ash is also going to leave the system as ash. So we don't need to worry about balancing it with all of the other byproducts. We're presuming, because it's a non-combustible, that it's not somehow going to bind with the other chemicals that we have in our fuel itself. Okay, so the enthalpy of formation for sulfur dioxide is given, because I think that one was not tabulated in our table, so they gave us that value. But if you look in table A26, the values for the other components are there. And we're just looking at the heating value of we'll end up looking at the products. Okay, so the first thing we have to do, because this is given in the mass or the gravimetric form, we have to convert everything to a molar form. So we're going to look up carbon, hydrogen, oxygen, nitrogen, sulfur, and our ash is also there. So carbon, if we assume we have 100 kilograms, we'll say it's 67.4 kilograms. Hydrogen is 5.31. Oxygen is 15.11. Nitrogen is 1.44. Sulfur is 2.36. Okay, so then we can look up the molar masses for each of those, which is in kilograms per kilomole. So we have 12, 2, 32, 28, and 32. And again, we don't care about the ash right now. Using this, we can calculate the molar number, which is the mass divided by the molar mass. So for each of these, 12 divided, or 67.4 divided by 12 gives us 5.617, 2.655, 0.4722, 0.514, 0.07375. Then, using that, we calculate Y, which is N over the total number of moles, and if we add up the total number of moles, we get 8.869 kilomoles. So we can calculate the Y value for each of those: 0.633, 0.2994, 0.0532, 0.0058, and 0.00832. Okay, so we did all of that just so that we would know the coefficients in front of each of those components in our equation. So let's go actually to the next slide. We can write that out, that if we're assuming it's complete combustion, 0.633 carbon plus 0.2994 hydrogen plus 0.0532 oxygen plus 0.0058 nitrogen plus 0.00832 sulfur plus our theoretical amount of air times O2 plus 3.76 N2. Okay, so those are all of our reactants. Our product is sum W times CO2 plus X times H2O plus Y times sulfur dioxide plus Z times nitrogen. Okay, so we go through the process similar to what we did before to find all of these coefficients. So we're balancing this side of the equation with this side of the equation. We find that W is equal to 0.633, X is equal to 0.2994, Y is equal to 0.00832, Z is equal to 2.774, and then the theoretical value for air is 0.7378. Okay, so now we want to find the mass of our fuel. So the mass of the fuel is going to be equal to the number of moles, or the mole fraction of each of these multiplied by their molecular weight. So this is finding the actual mass of the fuel, whereas before we assumed if we had 1 kilogram of fuel, then it would be these 67.4. Okay, we can't just add these up because we'll get 100 kilograms. What we need to find out is what our actual mass of the fuel is based on these new percentages. Okay, so the mass of the coal coming in is 0.633 times 12 plus 0.2994 times 2 plus 0.0532 times 32 plus 0.0058 times 28 plus 0.00832 times 32. Okay, so we're multiplying our molar number times the molar mass of each of those. So we get 10.33 kilograms. Then we can find our apparent molecular weight is equal to this 10.33 kilograms divided by 1 kilomole is equal to 10.33 kilograms per kilomole. Okay. So if we look at this, we can see, and if we remember from the previous slide, that all of these reactants are stable in their current forms, which means that their enthalpy value at the reference state, their H sub F value, enthalpy of formation, is equal to 0 for all of the reactants because we have carbon, hydrogen, oxygen, nitrogen, and sulfur. And in this table, we can see that they would all be 0. Sulfur's not listed, but it's also 0. So we just need to look at the enthalpy of formation for these products. But again, we have nitrogen here, so we don't have to worry about that one either. So we'll simply look at the enthalpy of combustion for these three terms, carbon dioxide, water, and sulfur dioxide. And when we calculate the higher heating value, we're going to look at water when it's in its vapor form. And when we look at the lower heating value, we're going to look at water when it's in its liquid form. Okay, so you can see on the table that has two separate values for water vapor and water. So water vapor is 241,820, and liquid water is a different value, higher value. Ooh, okay, so the higher heating value is going to be, if we look at H sub C, is 0.633 kilomoles times the heating value, or the enthalpy of formation for CO2. So we find that in the table is equal to 393,520 plus 0. I better look at my paper. 2,994 times negative 285,830 for water in its liquid form, plus 0.00832 times 297, negative 297,100 for the sulfur dioxide. That's the value they give us in the problem. So the enthalpy of combustion for the higher heating value is 337,147. It's a negative kilojoules per kilomole. And HHV is equal to a negative H sub C over the molar mass, or the apparent molar mass of the mixture. So it's this negative 337,147, that's a comma, divided by 10.33 kilograms per kilomole over that. So that gives us 32637.7 kilojoules per kilogram is the higher heating value for this particular coal. So then we perform the exact same analysis, but instead of having 285,830 for liquid water, we have negative 241,820 for water in its vapor state. And we do the same thing again, find the lower heating value is equal to 3,1 370 kilojoules per kilogram. So this is, I think, a lot less exciting than looking at steady flow engineering devices, turbines, pumps, things like that, chemical equations. But it does play an important role in thermodynamics because our heating source up till now, we just said, okay, there's a combustion process happening and we're getting some thermal energy in this amount, right? As you design these systems, you have to actually figure out what fuel to use, how much air to put in, how much thermal energy you can get out of it. So that's what we're trying to learn how to do.
That 10.33 kilograms.
Yeah.
Yeah, is that for the mass? Is that the mass of the mixture?
That's the molar mass of the mixture. Yeah.
So
The coal.
So that above it, that equation, that's for the mass. That's the mass.
Yeah, this is the mass of the fuel. So this, it's multiplying the kilomoles times kilograms per kilomole. So it's multiplying the number of kilomoles times the molar mass of each of these individual components. So like the hydrogen, the oxygen, the nitrogen, the sulfur, to find the mass.
So the molar mass of the mixture is the mass of the fuel over.
Yeah. Yeah. So, right. So that's basically what we're doing is we're saying, okay, some of our stuff has a molar mass of 12, some is 32. We see how many moles of each of those are in there, multiply it by their molar mass to find the weighted average of that.
Yeah, I was just wondering because you called that fuel, but it had the looks like the air or the oxygen and stuff in there. You didn't put that separate for that other one side.
Well, no, I didn't calculate the molar mass of the air.
Oh, okay. So all of that is part of the fuel as well.
No, this is not. I don't calculate that as far as the mass of the fuel.
I just meant the sulfur.
Oh yeah, that's the coal. That's the coal. So the coal has these components.